This is the kind of stuff that we repeatedly see. Last year, we were blocked, especially when we're seeing that we have a government that is actively blocking information from us.
The moment the scientific community blinked in disbelief was when NASA quietly acknowledged that the tail of R2 Swan behaves in a manner more reminiscent of propulsion than the usual plume of dust. That concession alone sent ripples through astrophysics and planetary science, challenging long-held assumptions about cometary activity in our solar system. What had been presumed as a dusty wake trailing behind a nucleus now appears to carry hints of directed thrust-like motion, something far more mysterious than mere grains of ejected material pushed by solar wind and radiation pressure. Before we start, hit the like and subscribe buttons for more updates. From the very first observations of comet C2025 R2 Swan, astronomers noted that its tail was unusually structured, exhibiting features sharper and more linear than the diffuse, fan-shaped tails typical of comets. Normally, comet tails consist of two major components: a dust tail, composed of small solid particles scattered by solar light and pushed outward by solar radiation pressure, and an ion or plasma tail, where ionized gas interacts with the solar wind to create a narrow, smooth trail. But R2 Swan's tail didn't neatly conform to those categories. It looked curiously too straight and coherent, as though something actively shaping or pushing it beyond passive mechanisms. When NASA itself admitted that the tail morphology aligns better with propulsion than dust, it signaled a profound turning point. The phrasing "more like propulsion than dust" implies that there may be internal outgassing jets or non-thermal processes generating directional thrust, far stronger than typical sublimation of ices. The raw data behind this admission remain under close study, but the implications are vast. We may have underestimated the diversity of comet behavior or overlooked exotic forces at play in our own backyard. To understand how radical this is, one must revisit standard comet theory. Comets are often described as dirty snowballs, agglomerations of volatile ices and dust. As they approach the sun, heat causes sublimation, turning ice directly into gas, which drags dust particles off the surface. The resulting coma and tails are passive consequences of that process. The dust tail follows a curved path dictated by solar gravity and radiation pressure. The ion tail aligns with magnetic and plasma flows. There is no need for directed thrust in the classical model. So when R2 Swan's tail behaves in a thrust-like way, we are being forced to consider more dynamic internal processes, perhaps episodic jets or even electrostatic discharges that create asymmetric outflows strong enough to push portions of the coma. The admission rescues a slew of observational anomalies that were otherwise dismissed or minimized. For weeks, telescope arrays around the world had captured images of R2 Swan with one side of the tail appearing unnaturally straight, or even showing kinks and sudden bends that seemed inconsistent with solar wind interactions alone. Some amateur observations hinted at apparent accelerations in tail direction that could not be reconciled with standard dust particle dynamics. Until the official acknowledgement, such strange behavior had been relegated to the odd but ignorable column. Now, those observations must be taken seriously. One immediate implication is that our models for comet nuclei and their subsurface volatile layers might be incomplete or oversimplified. The possibility exists that R2 Swan contains localized supervolatile reservoirs or structural conduits that channel gas in narrow jets, effectively creating a kind of built-in thruster. In effect, the comet might be steering its tail to some degree, rather than just letting solar forces shape it. That raises questions about internal cohesion, cryovolcanism, subsurface plumbing, and perhaps even non-uniform porosity or fractures capable of focusing outgassing. Moreover, this behavior might require us to revisit key parameters used in orbital calculations for comets. If a comet can exert small but sustained self-propulsive forces, then its trajectory over time may deviate subtly from predictions that rely only on gravitational dynamics and non-gravitational accelerations derived from symmetric outgassing models. For near-Earth comets or those crossing orbits near planets, even a slight misestimation of these self-thrust forces could lead to errors in estimating close approach distances or predicting long-term dynamical evolution. The propulsion-like tail also challenges the distinction between comets and other small solar system bodies, like active asteroids or main belt comets. We have already seen objects with intermittent activity or mass loss from non-traditional sources, for example, rotational breakup, sublimation of exotic constituents. If R2 Swan is among a class of comets with more pronounced internal jetting or propulsion, then our classification schemes may need to expand. We may even have overlooked other comets that exhibit similar behavior, but were too dim or far to detect such structure at high resolution. Another fascinating possibility this opens is that cometary bodies might, under certain conditions, modulate their outgassing in deliberate ways. Not deliberate in the sense of life or intelligence, but through feedback loops in pressure, thermal gradients, or internal fractures. Perhaps as one region becomes active, pressure builds, tunnels open, and new jets form, shifting the thrust vector and altering the tail orientation. R2. Swan's tail could thus be a snapshot of a dynamic, evolving internal system rather than a static process. If that is so, every comet we observe may have latent potential for such behavior, though typically too weak, masked by dust or blurred by distance. R2 Swan, because of its brightness and favorable geometry, may simply be one of the few where the phenomenon is detectable. In that sense, NASA's admission is not that R2 Swan is unique, but that our observational bias and theoretical conservatism have concealed a broader menu of cometary physics. From a broader astrophysical perspective, such behavior prompts us to reconsider outgassing physics in general. Solar irradiation, thermal conduction, sublimation rates, cavity formation, pressure dynamics, and material strength all interact in complex ways inside a comet. If propulsion-level jets are possible, we need new simulations and models that integrate directional feedback, jet focusing, time variability, and interaction with magnetic and plasma fields. The mechanisms that confine outflow into narrow jets, possibly narrow fractures acting like nozzles, deserve renewed scrutiny. One may wonder whether such jets could alter the shape and rotation of the nucleus itself. Persistent asymmetric thrust could impart torques, spinning up or reorienting the comet's rotation axis over time. That in turn would change the insulation patterns, feedback into which parts get heated or active, and perhaps lead to cascading structural shifts. In extreme cases, if internal channels migrate or collapse, they might trigger outbursts, fragmentation, or morphological changes in the nucleus. R2 Swan offers a dynamic laboratory to watch those processes in action. It is worth contemplating whether such active propulsion could affect how comets age or degrade. If jets can chip away material more selectively, they may open fissures, expose fresh volatile layers, or provoke structural weakening from within. Over multiple passes near the Sun, a comet with strong directional jets might erode in patches, lose mass non-uniformly, or even disintegrate more rapidly. Traditional models assume relatively symmetric mass loss. R2 Swan suggests that evolution may be far more chaotic. In turn, this raises implications for how comet dust and debris streams build over time. If jets preferentially eject particles in certain directions, the spatial distribution of dust released into orbit may be anisotropic. That could influence how meteor showers from a comet evolve, how debris trails disperse, and how subsequent orbital intersections with Earth's path occur. Some meteor showers might owe their structure to directional ejection rather than uniform release. Planetary defense strategies could also be subtly influenced. While comets are rarely immediate threats, accurate trajectory predictions are crucial over time. If comets can introduce unpredictable thrust components, then risk assessment must account for possible self-propulsion deviations. That underscores the need for closer observation, better modeling of internal processes even in long-period comets, and perhaps even spacecraft missions tailored to sample internal pressures or local jets. On the observational front, this admission will likely spark campaigns with space telescopes, large ground instruments, and even radar or interferometry targeted at detecting fine-scale structural motions or jet signatures. Polarization studies, spectroscopic analyses of gas flows, high frame rate imaging of tail oscillations or twisting, and time series photometry may help distinguish between pure dust and active thrust effects. Alternate hypotheses, such as solar wind interactions, magnetic channeling, or plasma instabilities, must be rigorously tested against the propulsion hypothesis. The burden now lies on observers to unambiguously document jet-like behavior, trace gas velocities, and measure deviations from passive models. In the context of the larger cosmic theater, R2 Swan reminds us that even in our well-observed solar system, surprises await. If a comet's tail can belie fundamental assumptions, then perhaps we should be open to new mechanisms in other small bodies, centaurs, icy moons, trans-Neptunian objects, and even interstellar visitors. The boundaries between comet, asteroid, and active body may be blurrier than we thought. A body might lurk in the Kuiper Belt or Oort cloud with latent, internal pressure systems, waiting for a solar trek to activate exotic jets. There is also a poetic twist. Comets have long been symbols of mystery, portents, and cosmic messages. That their tails may hide hidden engines only deepens the symbolism. Each tail might not simply trace the passage of the sun's energy, but whisper secrets of the body's inner machinery, forces, and history. R2. Swan's bold tail is a clarion. Look closer, expect the unexpected, revise your maps. Yet, we should temper excitement with rigorous skepticism. Alternate explanations, perhaps plasma instabilities, magnetic reconnection with solar wind fields, or even interactions with space dust streams, might mimic propulsion signatures. The community must critically explore these before embracing a wholesale paradigm shift. But NASA's admission has already shifted the baseline. The null hypothesis is no longer that tails are purely passive dust, but that hidden activity may lurk. The revelation surrounding R2 Swan's peculiar tail behavior has deepened not just scientific curiosity, but also philosophical wonder about the forces shaping the universe. When NASA admitted that the tail exhibits characteristics more consistent with propulsion than with the scattering of dust, it fundamentally shifted the way astronomers interpret active celestial bodies. Such an acknowledgement carries an implicit invitation to look beyond the ordinary, to imagine that nature itself is capable of producing effects that, until recently, we would have attributed only to artificial systems or deliberate engineering. R2. Swan's trajectory through the solar system has always been impressive in its brightness and visibility, but the discovery that its tail might be the result of active, directed forces gives its passage new meaning. The apparent thrust effect observed in the comet's tail suggests that internal processes could be exerting mechanical influence on its motion. Whether this thrust is the result of intense sublimation of volatile compounds or of more exotic mechanisms, it represents a form of natural propulsion operating on a cosmic scale. The implications for physics, planetary formation, and even the study of motion in space are profound. In the quiet darkness between planets, comets are often viewed as ancient remnants, archives of the early solar system frozen in time. Yet this event reminds scientists that these icy bodies are anything but static. They breathe, erupt, and evolve in real time, responding dynamically to sunlight, temperature gradients, and internal pressures. The propulsion-like tail of R2 Swan demonstrates that under certain circumstances, the interplay between thermal energy, gas release, and particle dynamics can create coherent motion that transcends the passive behavior expected from sublimating ice. Some researchers now suspect that what has been interpreted as propulsion could emerge from complex feedback systems within the comet's interior. As trapped gases heat unevenly, they might burst through narrow vents or fractures, creating intense localized jets. These jets would then act like miniature engines, exerting force in one direction and generating movement or acceleration in the opposite. On smaller scales, this might manifest as rotational acceleration or structural stress. On larger scales, as tail alignment that mimics a deliberate thrust vector. If multiple jets ignite in rhythmic bursts, their combined output could even create oscillations that alter the shape or trajectory of the ejected material. The remarkable aspect of this possibility is that it reframes the very definition of propulsion. In mechanical engineering, propulsion implies a controlled release of energy to achieve motion. In R2 Swan, there is no pilot, no mechanical apparatus, no control system, yet the outcome appears similar. Nature has discovered a way to generate directed momentum through nothing but the physics of sublimation and pressure differentials. If verified, this discovery could influence future propulsion research on Earth by providing new models for natural self-propulsion driven by uneven heating and venting. The geometry of R2 Swan's tail adds another layer of fascination. High-resolution imagery has revealed a tail that remains unnervingly straight over great distances, with variations that seem to pulse rather than diffuse. In most comets, dust tails broaden as fine particles spread under solar radiation pressure. Ion tails, on the other hand, trace solar wind lines and shimmer with a bluish hue. R2 Swan's tail, however, remains unusually narrow and bright, displaying coherent structure even where we would expect turbulence. Such geometry implies sustained energy input or a directional flow, the hallmarks of propulsion. One theory proposes that electromagnetic interactions could play a crucial role. The charged particles emitted by the comet might be aligning along magnetic field lines, amplifying the straightness of the tail. However, the intensity and consistency of the emission hint at something beyond simple alignment. If outgassing jets are sufficiently powerful, they could create a plasma sheath strong enough to carve its own path through the solar wind, an autonomous plasma plume with intrinsic momentum. Such a phenomenon would blur the line between physical propulsion and plasma dynamics, introducing a hybrid mechanism not yet fully understood. At a more fundamental level, this development forces us to rethink the boundaries of self-organized motion in space. The universe may harbor countless examples of bodies exhibiting propulsion-like effects driven by natural energy differentials. Astrophysicists have long observed outflows from protostars, jets from black holes, and plasma streams from magnetars, all powered by intense magnetic or gravitational fields. What makes R2 Swan's case unique is that it occurs on a vastly smaller, more tangible scale within the reach of our telescopes and perhaps one day our spacecraft. It is as though the comet is demonstrating a microcosmic version of the processes that shape galaxies. The potential for this discovery to inspire new technology is immense. If the physical principles behind R2 Swan's propulsion-like emissions can be replicated or understood, they could inform the design of propulsion systems that rely on thermal differentials and gas expansion rather than combustion or ion acceleration. Engineers studying space propulsion might find in this comet a natural analog for self-sustaining motion systems, especially those using sublimation or venting of volatiles in vacuum environments. In essence, R2 Swan could become a case study in cosmic engineering, an example of how simple thermodynamics can generate complex directed movement without mechanical parts. Yet the intrigue extends far beyond engineering. The discovery challenges fundamental astrophysical assumptions about comet behavior and energy budgets. Traditional comet models assume a largely isotropic release of gases, meaning the ejection occurs in all directions, resulting in negligible net motion. For R2 Swan, the observed asymmetry implies that energy release is far from uniform. Internal structure may concentrate gas in tunnels or fissures, channeling it in specific directions. This could suggest that comet interiors are more organized than chaotic, containing layers or networks of pores that shape the path of escaping material. If such structures are common, it would mean comets possess an inherent ability to regulate their activity in response to environmental conditions. When one vent activates, it might relieve pressure in nearby cavities, shutting them down temporarily. When solar heating shifts to another region, a new vent might erupt. The result would be a complex, pulsating rhythm of activity that mimics the cycle of an engine. Observing this on R2 Swan gives planetary scientists a new framework for understanding comet evolution and longevity. Rather than being passive aggregates slowly sublimating away, comets could be dynamic systems balancing energy and pressure through natural feedback loops. Spectroscopic observations of R2 Swan have already revealed peculiarities in the composition of the ejected material. Unusual ratios of carbon monoxide and carbon dioxide relative to water vapor hint at reservoirs of deeply buried volatiles being released through focused jets. These molecules, when exposed to sunlight, sublimate explosively and create high-velocity streams that could easily mimic the appearance of propulsion. If the composition varies over time, it could indicate layers of different materials venting sequentially, another hint of internal complexity. This interpretation also reshapes how we understand the origins of such bodies. If R2 Swan was formed in a region of the solar nebula with unusually high concentrations of volatile ices, then its propensity for intense outgassing would be predictable. But if its composition is not unique, then the event implies a universal potential for propulsion-like behavior in many comets, depending on their current thermal state and structural configuration. Either possibility alters how we view the distribution and activity of small icy bodies across the solar system. From a methodological standpoint, the discovery represents a triumph of persistent observation. For decades, astronomers have cataloged comets, often dismissing subtle anomalies as measurement errors or optical illusions. The idea that a comet's tail could display thrust-like characteristics would have seemed fanciful, but the accumulation of precise imaging, time-lapse monitoring, and spectral analysis has now built a body of evidence too substantial to ignore. NASA's acknowledgement was the culmination of years of incremental discovery, each piece of data eroding the conventional understanding of how cometary tails behave. In many ways, this shift mirrors other scientific revolutions. Throughout history, anomalous observations have forced humanity to reconsider the cosmos. From the irregular motions that hinted at planetary gravitation, to the strange orbits that revealed relativity, to the flickers of light that announced exoplanets, R2 Swan's tail joins this lineage of anomalies that compel humility. It demonstrates that even in a solar system mapped and modeled to exquisite precision, surprises remain hidden in plain sight. Perhaps the most captivating consequence of the propulsion interpretation lies in how it reframes our perception of motion itself. The comet becomes not merely a passive traveler, but an active participant in its journey, propelled by internal energy rather than solely by gravitational fate. The universe, once thought to be a theater of inert bodies following prescribed paths, now appears more like a vast ecosystem of entities capable of self-driven evolution. Even without intelligence, natural processes can imitate purposeful movement, suggesting that the boundary between organic and inorganic dynamism is thinner than previously imagined. This revelation could also affect how we search for signs of extraterrestrial activity. Scientists have long debated whether anomalies in celestial motion might one day hint at artificial origins, perhaps alien probes or engineered objects moving in ways inconsistent with gravity alone. With R2 Swan, we are reminded that nature herself can produce behaviors eerily similar to those we would attribute to intelligence. Understanding this will make future detections of genuinely artificial activity more robust by providing a deeper catalog of natural phenomena capable of mimicking propulsion. For planetary scientists, R2 Swan also raises the prospect of revisiting past comet data with new eyes. How many other comets have displayed similar, though less pronounced, behaviors that went unnoticed or unrecorded? The historical record is filled with comets whose tails changed shape unexpectedly, twisted in impossible directions, or displayed brightness variations inconsistent with solar illumination. These could now be reinterpreted in light of R2 Swan's behavior, forming a new category of active thrust comets. Such a class could redefine our understanding of small body mechanics and serve as a benchmark for future surveys. Technological innovation will follow naturally. Missions could be designed to fly through or near such comets to directly measure thrust forces, gas composition, and ejection velocity. Instruments capable of detecting microaccelerations or internal pressure fluctuations could verify whether propulsion-like activity truly exists. A dedicated probe could ride the comet's outflow, using its jets to adjust position autonomously, essentially harnessing natural propulsion for exploration. The data would not only validate theoretical models, but also provide practical insight into how naturally generated momentum could be exploited for space travel. R2. Swan's peculiar behavior may also offer analogies for phenomena beyond the solar system. Exocomets observed transiting distant stars have shown dips in starlight and dust tails that defy conventional explanations. If natural propulsion mechanisms exist, they might account for the irregularities in light curves and orbital paths seen in those systems. What we observe close to home may thus serve as a Rosetta Stone for interpreting distant cosmic activity. From a philosophical perspective, the admission of propulsion-like dynamics in a comet invites reflection on how humans interpret evidence. The distinction between coincidence and cause, pattern and purpose becomes blurred when natural systems imitate design. The mind instinctively seeks agency behind movement, yet, in R2 Swan, agency arises purely from physics. The comet becomes a metaphor for complexity emerging without intent, a mirror to life itself, where order and directionality arise spontaneously from chaos. On the scientific front, research will now focus on quantifying the thrust and energy balance involved. If R2 Swan's tail truly embodies propulsion, then measurable momentum changes should appear in its orbital data. Precise tracking of its trajectory over time could reveal minute deviations consistent with internal forces. Early hints suggest such deviations exist, though distinguishing them from solar radiation pressure requires extreme precision. Even so, each observation tightens the net of evidence, gradually transforming speculation into established fact. The modeling efforts are likely to evolve in tandem. Computational astrophysicists are building simulations that treat comets not as isotropic emitters, but as dynamic systems with localized jets, rotational feedback, and material anisotropy. By feeding in the parameters observed in R2 Swan, they can test whether natural outgassing alone could reproduce the observed tail geometry. If not, then more exotic mechanisms, perhaps electrostatic acceleration or plasma resonance, might need to be invoked. Each hypothesis carries implications that reach beyond cometary science, touching upon plasma physics, magnetohydrodynamics, and even the study of exoplanet atmospheres. What makes this chapter in space exploration especially compelling is that it occurs in real time before our eyes. Humanity stands at the intersection of discovery and mystery. Every new image of R2 Swan reveals nuances that deepen the story. Subtle undulations in the tail, flickers of brightness that suggest pulsing emissions, spectral shifts indicating variations in gas composition. It is as though the comet is performing a cosmic ballet choreographed by forces still half understood. For every answer found, another question unfurls behind it. Scientists must now confront a delicate balance between excitement and rigor. The term propulsion carries weight, and to apply it to a natural object demands caution. Yet caution must not smother curiosity. The admission by NASA does not finalize the debate, it opens it. It acknowledges that what we are seeing cannot be fully described by existing dust and plasma models, that something new is at play. The pursuit of that something will define a generation of cometary science, just as the discovery of non-gravitational forces once revolutionized celestial mechanics. The ramifications even extend to education and public imagination. Students who once viewed comets as passive visitors will now see them as living laboratories of physics. The story of R2 Swan can inspire a new era of curiosity about the hidden processes within seemingly simple objects. It illustrates that discovery often begins with noticing what does not fit, with refusing to dismiss the improbable. For the public, it rekindles a sense of cosmic wonder, the realization that even familiar patterns in the sky may conceal unsuspected power. Astrobiologists are also taking note. Although there is no suggestion of biological activity, the internal energy cycles implied by the propulsion-like tail suggest environments of transient warmth, pressure, and chemistry. Within such environments, complex organic reactions could occur more readily than previously believed. Comets like R2 Swan may thus be not only couriers of prebiotic molecules, but active reactors that modify those molecules through heat and radiation. In that sense, propulsion-like jets could play a role in shaping the chemical landscape from which life eventually emerged. Beyond biology, the aesthetic and symbolic power of this event cannot be overlooked. Humanity has always associated comets with omens and transformation. In ancient times, a strange tail in the sky would have stirred myths and fears. Today, it inspires awe grounded in science. The fact that NASA itself acknowledges the anomaly lends it gravitas, a signal that mystery still thrives even in an age of precision instruments. R2 Swan stands as a reminder that wonder and knowledge are not opposites but partners in discovery. As observation continues, the comet's changing behavior will serve as a natural experiment. If the tail's alignment or intensity varies with its distance from the Sun, researchers will gain insights into the dependence of the propulsion effect on solar energy input. If it persists even in cooler regions, then internal processes independent of sunlight must be at work. Each outcome tightens the circle of possibilities and deepens understanding of the underlying physics. Perhaps one of the most far-reaching consequences of this finding will be its influence on how humanity perceives motion in the cosmos. Once every object was thought to move solely under external forces, gravity, radiation pressure, or collisions. Now we glimpse the possibility that even small bodies possess intrinsic engines powered by internal energy gradients. The solar system becomes less a clockwork of predictable paths and more a dynamic web of interacting agents, each shaping its fate through internal dynamics. In a universe that spans billions of light years, it is humbling to realize that even a small comet can challenge human understanding so completely. R2 Swan, gliding silently through space, embodies the dual nature of science itself, the constant tension between explanation and mystery. Each observation erodes ignorance, but also expands the horizon of the unknown. The tension drives progress, urging scientists to look deeper, to refine instruments, to test new ideas. As telescopes continue to track R2 Swan's passage, data will accumulate, theories will evolve, and debates will flourish. But regardless of the eventual verdict on the exact mechanism behind its extraordinary tail, the event has already achieved something rare. It has reawakened the spirit of genuine discovery. It has shown that even in the age of robotic probes and high-definition surveys, the cosmos retains its ability to surprise, to whisper that there are still phenomena waiting to be understood. NASA's acknowledgement of the propulsion-like tail marks not an end, but a beginning, a threshold between known and unknown physics. It invites scientists to listen more carefully to the language of the universe, to recognize that the smallest anomalies can herald the grandest revelations. And as R2 Swan sails farther from the sun, leaving its luminous trail etched across the darkness, it carries with it the promise that the story of cosmic motion is far from complete. Each flicker of its tail is a reminder that the universe is not merely observed. It is alive with forces, patterns, and mysteries still unfolding beyond the reach of certainty. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on NASA's shocking R2 Swan's propulsion claim? We want to hear from you. Thank you for watching, and see you next time.